Hello guys, so today we'll be discussing about message authentication. Message authentication broadly means that it is a mechanism or service which is used to verify the integrity of the message. That is, the message is not modified and there is no deletion, there is no updation onto the message, there is no new insertions on the message, and the message received by the receiver is exactly same as the message sent by the sender, and it also ensures that the message is coming from the valid user or the intended source and not from any third party, right? So this is the main purview of message authentication, but before directly going into the message authentication part, let's try to analyze what are the kind of attacks that are generally made in context of communications across the network. So the attack on disclosure and traffic analysis attack, that is basically on the confidentiality of the message, that the message is somehow getting exposed to the person who is not holding the valid keys, or in other words you can say the message is getting exposed to the unauthorized person. Source repudiation and destination repudiation, as we had seen in the previous video also on digital signatures, that it was providing you an additional service in conjunction with the trusted third party about the non-repudiation, and therefore if there is the denial or a claim by any person that an event has occurred or not occurred, that could be proved with the help of non-repudiation services, and that comes under the purview of the digital signatures. So masquerading, the content modification, the sequence modification, the timing modification, all such attacks comes under the purview of the message authentication, and also digital signature to some extent, because as we had seen in the previous lecture, digital signature was making sure that the message is coming from a valid user, and the public key crypto system is used in such a way that the receiver basically verifies that the message or the signed document is coming from the valid user. So not just the validity of the user was proven, but since you were able to reproduce the same content from the signing the messages, the message integrity was also offered by the digital signature. So if there was any modification, the signatures would not have mapped. So digital signature is by default, taking care of these attacks, and this also comes under the purview of the message authentication. So message authentication is a procedure to verify that the received messages come from the alleged source and have not been altered. And message authentication may also verify sequencing and timeliness. Digital signature is an authentication technique that also includes measures to counter repudiation by the source. So authentication function basically consists of two things, the authenticator and the verifier, and we had seen this in the digital signature as well, that the receiver is basically the verifier with the verifying algorithm. So authenticator is a function that produces a value that is to be used to authenticate the message. So that means there will be a function that will be providing a code which will be appended with the message, like we used to append the sign with the digital signature. And the job of the verifier will be similar to the one that we had seen previously, that when you receive the message, you try to create the code, and if the code matches with the code that you have received, that means the plain text has been verified, and then you accept it. So these two are the main ingredients of the message authentication protocol. I can again say digital signature is also an authentication technique. Whatever we had seen in the previous video, a similar kind of an approach would be seen here as well. So the type of authenticator functions are message encryption, message authentication code, and hash function. Message encryption is basically of two types, as you know. The first one is your symmetric key. So if A and B are the source and you want to send a plain text to B, you basically encrypt it using a key K, and you get an output as EKP, which is then decrypted by the B, and B gets the plain text. Now in this situation, since K is the shared secret between A and B, right? So if A wants to send a message to Z, then a separate set of key would be used for the encryption and decryption when you're talking to some other person. So this K is basically the shared secret between A and B. So if B is able to decrypt by the shared secret that it shares with A, that pretty much means that you are getting the message from the A. So in a sense, this not only provides me with confidentiality, but it also provides me with the authentication. But there is a problem. The problem is that this decryption algorithm that we have with the B, this would be able to decrypt any message coming from any source. So if there is an intruder that sends a message to P, the B would be able to decrypt the message with using this K. The problem here is that the message once get decrypted may result into some haphazard values, because the K used by the intruder would be some K dash value which is not equivalent to K, and therefore when you are decrypting that message you would be getting some random string. Now the B is literally confused whether A has sent a message that is jumbled up or the intruder is trying to send a message. So B would be getting the jumbled up plain text after the decryption operation. The situation could be that jumbled up sequence of P is because it is coming from some intruder which is encrypted using some K dash value, or it could be that A is sending you a message that is all jumbled up. Now in both the situations you have to make an intelligent decision at B whether you have to accept that message or not. Therefore, this scheme by default is not providing you any such facility, right? So you have to make a decision whether you are accepting the plain text or you are not accepting the plain text. For that you have to understand that what meaning that plain text is imparting to B. This could be done with the help of another mechanism, and that is called as the internal error control, where you pass this P with a function f, and this function f is called as the frame check sequence. This is equivalent to the checksum that you must have studied in your networking course last year, where you know that when you are calculating the checksum, then basically you take the 64 bit or whatever bit stream you have, you place them in the column of 16 bit values, and then you XOR them. So the value of 1000 something, and then you have got, you just break them down into 16 bits, write one below the other, and then you simply perform an XOR operation. The resultant value will be a code, a checksum code. The similar approach is used with this function f over here as well. So this frame check sequence is basically a checksum that is calculating the checksum value for the plain text, and that checksum value is then appended with the plain text. So this becomes the overall message that should be encrypted with the help of the shared secret between A and B, that is K. So this is, after encryption you are getting a message which is a combination of plain text and the checksum code that is attached to it. So the first operation you perform at the receiver's end, that is at B, is decryption using the same shared secret key K, and once this is performed you will be getting a sequence of P and FP, that is the code. The second thing you need to do is to verify the message, and for that you will be passing the plain text through the same frame check sequence function, thereby generating the code for that plain text, and then you will be comparing that the code that you have generated and the code that you have received, they match or not. If they are matching, that means not a single bit has been modified in the message. The scheme that I told you about, this checksum, was the most simplistic one. There, if you are changing more than one bit, strategically the code will be same, but there are much more complex functions that achieve that a slight change in the bit would be reported and the same code will not be generated. Therefore, just imagine a function that is calculating such a code, and if the code are matching, that means the bit stream has not been modified under the path. So this is also called as internal error control, because it is first adding some text to the plain text and then it is encrypting, right, and then you are forwarding it. The key point over here is that this code is basically telling you one thing, that the message integrity has been maintained, nobody has modified the message. If the message is coming from the intruder, the thing would be that if when you are generating the code, that code would not be matching the last bits attached to it. because intruder's message when decrypted will be resulting in some P dash message. In that P dash, you will automatically assume that the last bits are going to be the code. Now, it is very improbable that it is very unlikely that any random sequence of bits would exhibit the desired relationship, right? Therefore, this is going to be the f function of P dash. This is very unlikely to happen, and therefore, this scheme is pretty much in identifying that the message is coming from the authentic source and there is no modification onto the message, and therefore, the message would be accepted by the receiver. The other way is that the plain text is first encrypted, and then on that encrypted value you calculate the code, you merge both the values and forward it to B, and at B the first task you perform is that you calculate the code by yourself. If that code matches the code that is appended on the transmission, then you accept and you go for decrypting the code using the same shared secret. And you should get the plain text back that you will accept. Now, this is called as external error control, because here you are performing the encryptions first and then moving on to add codes to it and thereby moving forward. This function f can also in some of the textbooks referred to as MDC or modification detection check, which is basically a bit stream or a code that is detecting if some of the bits of the plain text have been modified or not. It simply assumes that if some of the bits are modified or even one of the bits is modified, the code is going to be entirely different. If we are talking about message encryption where private and the public keys are used, that is public key crypto system, then the simplest case is that you are encrypting some message with the help of the public key of the Bob, and then you at the receivers and that is B, you are decrypting with the help of the private key. Since you are using the private key over here, it makes sure that the message was encrypted by the public key of B. Now, public key is accessible to anybody in the world, therefore, you cannot authenticate that the message is coming from the specific person, because anybody in the world can have your public key and can send you the message, right? But confidentiality is maintained because this message cannot be read by any other person, it can only be read by the person who holds the private key of B, and which we assume that is only available with the B and it has not been compromised. The second method is that you encrypt using the private key of yourself and then you forward it to B. Then B needs your public key to decrypt the message. Now here B is quite sure that the message is coming from the source that holds the private key of A, and therefore it is authenticated that the message would be coming from A. This approach we had seen in the digital signature. So, it provides you with the authentication and digital signature, but it doesn't provide you with any confidentiality. If you want to have confidentiality and authentication both, this is a task. Just try to design a scenario where both the services could be offered at the same time. Message authentication code is in short called as MAC. This MAC is basically a function, and this function has got some key value which helps in the calculation of this MAC code over a plain text P. This key is also supposed to be a shared secret between the two users who are communicating. So, you got a plain text, you pass it through the MAC function and you use K1, and that K1 will give you the MAC code which is represented by M, K, P, that is K1, P, which is appended to P. This is very similar to the approach that we had seen previously with the internal and external controls. Now, this P is forwarded to the B. At B, the first task you perform is that you pass that plain text using the same shared secret K1 through the MAC code and get the value of MAC, that is M. You compare both the values. If these two values map to each other, then that means you are accepting the message, and here you are getting the service of the message authentication. If you are encrypting this message MK1P with some other key K2, which is the shared secret between the A and B, So B would be decrypting the value first, thereby getting the value of P and MK1P. Again, at this point it will be passing the P through the MAC function, thereby calculating the code and comparing if the code matches. So in this case, a message authentication is also providing you with the confidentiality, and here authentication is basically tied to the plain text, because it is the plain text that is passing through the M function to get the MAC codes, right. Now this diagram is quite similar to the one that we had seen with the internal error control. On the other hand, you can first encrypt your P with some shared secret K2, and that encryption can be passed through MAC function. You append both of these and pass it on to B. Now at B, the first thing you perform is calculate the MAC of the encrypted value that you have. If the code matches, then you have to perform the decryption using the shared secret K2 and generate the value of P in order to accept it, right. So here you are getting the message authentication and the confidentiality, but now in this case your authentication is tied to the ciphertext that you had calculated, right. So what is this MAC authentication function? So receiver and sender know a shared secret, that is K. So the receiver is assured that P is from the alleged person, right. Receiver is assured that P is unaltered. If P is altered and not MAC, then the MAC calculation at the receiver will be different, and the MAC output length is fixed. That means whatever is the size of the input it has, the output is also always going to be a fixed length output, right. And MAC is not necessarily reversible, and therefore MAC cannot be said to be an encryption algorithm, because an encryption algorithm is supposed to be reversible in nature. MAC is many to one function, because now you see that MAC has got a separate key for itself. So if you have got a message that could be represented with 128 bits, and MAC if it could be represented only with the help of 16 bits, and here we also said that the MAC output is fixed length. That means output is in 16 bits, message could be in 128 bits, message could be in 4 bits, right. So if the message is represented by 128 bits, that means you have got 2 to the power 128 messages, and for those you can only generate 2 raised to the power 16 MAC values, right. That means one MAC value will be there for 2 raised to the power 112 messages. So there are 2 raised to the power 112 messages that will be having the same MAC value. Now furthermore, if this MAC value is since it is calculated with the help of the K value over here, and if this K is represented by 8 bits only, then you will have 2 raised to the power 8 different mappings from the set of messages to the set of MAC values. Therefore, there will be many messages with the same MAC values. That is one of the things with the message authentication code. The attack on code, number one, is your brute force. The brute force, it appears that it is an easy attack to be made on MAC, but it's a difficult one. You know, in case of brute force, the security is generally dependent on the bit length of the key, but MAC function is many to one function, as we had seen in the previous example. Now, if we suppose that the key size K is greater than the MAC size, in the previous example we had seen the key size is less. If it is greater than the MAC size, then what would happen? So that means that a total of 2 raised to the power K max can be produced, but since the value of K is greater than the value of N, that means maximum number of max that you can generate is 2 raised to the power N, and 2 raised to the power N is a value which is smaller than the value of 2 raised to the power K. Therefore, you can have 2 raised to the power N different max. Thus, a number of keys will produce the correct MAC, leaving the intruder clueless. Let's look with the help of an example. On an average, you require 2 raised to the power K minus 1 key values that will produce a match. For example, if you have got a message M1 and you have got a MAC1, you calculate with the help of the function M, and the MAC code is coming out to be MAC1. Then you compute mac I for all the values of ki. So there are 2 raised to the power k different keys. So for all the keys you calculate those values. The number of matches that you get is equivalent to 2 raised to the power k minus n keys. So what does this essentially means is our n is less than k. So 2 raised to the power n max would be generated, which will correspond to 2 raised to the power k keys. This is a large value, this is a small value. So we can say that one mac will be represented by 2 raised to the power k divided by 2 raised to the power n keys, which is equivalent to 2 raised to the power k minus n keys. So one mac value is mapped to 2 raised to the power k minus n keys. This is what essentially is shown over here. 2 raised to the power k minus n keys जो हैं वो सेम मैक्स को जनरेट कर सकते हैं. तो देयर इज अ कंफ्यूजन. द कंफ्यूजन इज दैट विच इज द की दैट इज यूज्ड बाय द सोर्सेज A and B, and your target is to find the exact key which was used for the calculation of the MAC, but you are given with an option of 2 raised to the power k n minus 1 keys. This is also called as pigeonhole principle, where you have got limited number of spaces and more number of pigeons to adjust to, and therefore there are instances where 2 pigeons will be sitting onto the same cell that is created for them, right? Similarly, you have got a number of keys and a lesser number of MAC values. So the cells over here are the MAC values that you can generate, and the pigeons is the keys that you can generate. So if you have got more number of keys, that means more than one keys will be using the same MAC value, right? So if you are given a MAC value as in this case, and you want to identify the key, you will not be able to get a unique key, but there will be some keys that will be sharing the same MAC value. And when you repeat this process again with some message M2 and you calculate the MAC2, now after the generation of all the ki values for the 2 raised to the power k minus n keys, the result would be again 2 raised to the power k minus 2n number of keys. Why? Because now you have got the maximum domain to be 2 raised to the power k minus n keys, and the MAC could be generated with the help of 2 raised to the power n values. So after the completion of this round, the number of keys that would be left with you are 2 raised to the power k minus 2n keys. And if the more number of rounds that you complete, the lesser number of keys you get in every round, and eventually you will be getting a single key that would be the key used for the calculation of the MAC for a particular intercepted MAC values. So if MAC is 32 bits and the key is 80 bits, then in round number 1 you will be getting 2 raised to the power 48 number of keys producing the same MAC value. In the second round you will be getting 2 raised to the 16 number of keys getting you the same MAC value, and in round 3 should produce you a single key that corresponds to the MAC value that you have intercepted, right? So the requirement for the calculation of these MAC value is that number 1, it should be infeasible to compute P dash in such a way that that particular P dash produce the same MAC values as it was produced with the plain text P. So that means nobody should be able to replace the plain text in such a way that the MAC values remain the same, because in our MAC scheme we said that code is the thing that basically identifies if the message has been modified or not. If somebody is able to generate the same message with a same code with this different message, then it is a big problem, because anybody can now change the plain text, enforce a new plain text P dash, and with the same code can forward it to the destination B. So this is one of the requirements, that no other value of the plain text should be able to produce the same MAC value. The second requirement is that the probability of finding any P dash which gives you the same code as in the case of PK should be with a very low probability. The probability is of the order 2 raised to the power minus n, where n is the number of MAC values that you can generate. So if MAC is 32 bits, that basically means 1 upon 2 raised to the power 32 should be the probability for the each MAC value that you are generating with respect to the plain text. So the probability of finding the plain text p dash that produces the same MAC value should be a very small figure. And the final requirement is that the authentication algorithm should not be weaker with respect to certain parts or bits of the message than the others. For example, you have got a plain text P, and if I deliberately modify certain keys of that plain text and try to create a plain text P dash, then there is a good chance that I would be able to generate the same MAC values. My argument here is that the algorithm that we had seen where we were using the function f, and if function f was the XORing component of 16 bits of data blocks, and then in that case, as I said, because it was maintaining a parity count, and therefore if in a column if I am changing two values or toggling two values, then the code comes out to be exactly the same. If I know that particular problem with your scheme, then I would be able to transform the plain text to some p dash text in such a way that that p dash supports me in certain kind, and then I can forward that p dash instead of the plain text p with the same code, and the person will not be able to identify. In order to thwart such kind of an attack, again, the probability of any new message and the probability of finding a MAC value with the p dash should again be a very less value of the order 2 raised to the power minus n. तो मतलब कोई भी आप मैसेज अपना जनरेट नहीं कर सकते तो सेम मैक वैल्यू दे दे, या आप किसी प्लेन टेक्स्ट को स्पेसिफिकली कुछ बिट्स को चेंज करके एक ऐसा मैसेज में कन्वर्ट नहीं कर सकते जो कि सेम मैक वैल्यूज़ को प्रोड्यूस करे. ऐसा आपको स्कीम मैक का रखना चाहिए. इसलिए जो चेकसम वाला स्कीम दैट वी हैड सीन वो यहाँ पर इम्प्लीमेंट करना अच्छा नहीं होगा, क्योंकि वो मैक की सेकेंड और थर्ड रिक्वायरमेंट्स पे फुलफिल नहीं हो पाएगा. सो यू नीड टू हैव बेटर एल्गोरिथम्स for the MAC calculations. Hash function is quite similar to your MAC function, but the difference is that it is not using a key. It is a one directional function that produces a hash code or a message digest, and it is represented by the H in the bracket plain text. The principal objective is again here data integrity, because when this code is getting attached to any message, it has to be verified by the receiver by producing the same code. If the code matches, that means the message was not modified at all. So data integrity is the basic functionality offered by the hash function. It is also a one-way function. That means once you have calculated the digest of a message, you cannot get the message back from that digest. So you can only have one directional flow with respect to the hash functions, and it does not use key, therefore it is a bit different from the MAC function. It defines a function in such a way that even one bit of change in the input should completely change the hash code that you are getting at the end. These hash functions, now you will get the similar diagrams as in the case of MAC function, but here the function is represented by H. So you are converting you are calculating the code of the plain text and you are appending it. So P and HP would be encrypted then and forwarded to the Bob, and the Bob will decrypt it, get the P and HP. B would be forwarding the P through the hash function to calculate the code. Will try to match the code calculated by B and the code supplied by A. If they both compare, then the message P would be accepted. So this is providing you with authentication and confidentiality, both authentication with the help of the hash function and confidentiality with the help of the encryption function. The encryption over here is the bit key encryption. The other case could be that you have calculated the code, you have encrypted the code, and then the encryption of that code is attached with the plain text P. So when it is now forwarded, you have to pass your P with the hash function, which will produce the code, and then you have to decrypt the code that you had encrypted from here with the help of the shared secret key, that is K, and you will get the HP again. And if these two values equate to each other, then that means that the message has not been modified and will be accepted by B. So, this particular scheme is providing you with the authentication, and it is not providing you with the confidentiality, because the message is transmitted directly over the insecure channel. Here also the code is encrypted with the help of symmetric key encryption, and this code reduces the processing burden for those applications that do not require confidentiality and only require with the authentication. Then we have got a case where hash key or the code, hash code, is encrypted with the help of the private key of A, and then it is forwarded to B, and B decrypts it using the public key of A. So, what happens over here is that confidentiality is not there, but digital signature is fulfilled along with the authentication requirement, because it is comparing the hash codes. That means it is authenticating, and it is using the private and the public key, that is a digital signature. And digital signature means that the message thus generated could not be generated by any other value, because it is generated with the help of private key of A. Now, if you want to provide confidentiality to this scheme, all you need to do is you have to place an encryption algorithm before moving your text onto the insecure channel, and therefore the diagram would look somewhat like this: that you have got a plain text, you calculate the code, and that code is encrypted, then you append both the plain text and the code, you pass it through the encryption algorithm, and then you pass it on to the insecure channel, you decrypt at the B, and then you repeat the same process as in the previous case for the verification of algorithm as well. So, if confidentiality and digital signature both are required, then this particular approach should be used. The fifth scenario is that it is possible to use a hash function, but no encryption for message authentication, and that is with the help of a secret that is shared between A and B. Now, this technique assumes that the two communicating parties share a common secret, which is represented by SEC over here. Here A computes the hash value over the concatenation of the secret value and the plain text, and this appends the result, and then it forwards it on to the insecure channel. And when it is received by the B, the first thing that B has to do is it has to get the value of P and the secret information that it knows. It appends both of them, thereby generating the value somewhere around here and passing it through the hash function to generate the code. The code that's generated should be able to map to the code that is attached with this message. Fine. If these two are equal, then you accept the message. So, this particular diagram is providing me only with the authentication, and there is no confidentiality, there is no digital signature. The other thing could be that you are looking for confidentiality to the same scheme. So, this could be added by simply providing an encryption function at this point somewhere, so that the P is not forwarded onto the insecure channel as is, and therefore the initial process of calculation of code and appending it with the plaintext is same. You pass it on through the encryption algorithm, and then the encrypted form is forwarded through the insecure channel. You decrypt the values at the B, and you again apply it with the secret information that you know along with the P, and calculate the hash values, compare it to the hash values that are provided after the decryption that you have received over here, and therefore this scheme is now providing you with the confidentiality and authentication both. The requirement for hash functions is that hash function can be applied only to the block of data, and that block of data could be of any size. It always produces the result in a fixed length output. So, whether the input is 4 bits or 400 bits, it does not matter, it will always be giving you the same fixed length output. The calculation of the hash code should be an easy task for any given x value, and it should be a one-way calculation. This one-way property is also called as the pre-image resistance, where if I am providing you with any hash code, then it should be computationally infeasible for you to find the value of the message. So from hash you cannot get the value of the message. So this is your one-way property. The other is that if I give you a combination of the message and the hash code corresponding to it, you should not be able to find any other message y which is not equal to the message x such that the code of both the values match. And this is one of the requirements that we had already seen in the Mac. So the same requirement comes over here with the hash functions as well. Is called as the second pre-image resistance or weak collision resistance. The third one is that if you do not have any information, then you should not be able to find a pair of message x and y such that the code of x and the code of y are same, right? So it should have a strong collision resistance. There should not be collision. Here collision means that for any message, if you are calculating the code should not be same. If the code is same, that means a collision has occurred, right? So it should not have any collisions. The simple hash function could be that you have received input of n-bit blocks, and this input is processed one block at a time in the iterative fashion to produce some n-bit hash value. Bitwise bit operation are generally the XOR operation performed on every block. So you calculate the ciphertext with the various bits that you have got as an input, and then you produce a simple parity for each position. This is known as longitudinal redundancy check. The approach over here is very similar to the one that we have seen in the case of FCS, that is a frame check sequence, where we talked about checksum. And this function is reasonably effective, but not a very good function as we had seen, and you would be able to predict the formatted data, and the function is very less effective. So if you want to improve this function, then one way is that you should be performing the circular shifts at every round. So what happens now, this is the overview, that you have got a message n, you break that message into the equal length n bits. If the last one is not able to get to the n bits, you pad certain values to it to make it n bit long. You will be having an initial vector, that is iv, with certain initial hash values. These hash values will be XORed with the first set of block, and after XORing, whatever result you are getting, that result would be your H1. This hash 1 value will pass on and get XORed with the next set of block, and while you are doing so, you have to perform a shift left operation as well. So the initial set is n-bit hash value iv, that is initially 0. Rotation function is applied onto every function that is used for XORing, and what this necessarily does is that it has got a randomizing effect on the input and a more complete effect onto it, because after every shift you will have a new set of values which will be XORed with the next set of blocks. So the effect of one bit will be on several other bits as we are circulating. So this addition of simple circular operation has achieved a much improved version, because now one bit would be affecting many other bits after getting shifted. It has the effect of randomizing the input more completely and overcoming any regularities that appear in the input. तो अब यहाँ पे सर्कुलर शिफ्ट को ऐड करने का जो सबसे बड़ा फ़ायदा ये है कि पिछले केस में चूँकि हम सिंपल एक्सॉरिंग परफॉर्म कर रहे थे, एक्सॉरिंग परफॉर्म में हमें मालूम पड़ा था कि हमें पैरिटी वैल्यूज़ मिलना शुरू हो गए। तो पैरिटी वैल्यूज़ में हमें मालूम है कि हम अगर एक ही कॉलम की बात करें तो हम 2 बिट्स को अगर टॉगल कर देते हैं तो हमारी पैरिटी वैल्यूज़ कभी चेंज होंगी ही नहीं। तो इस वजह से अब अगर हमने शिफ्टिंग परफॉर्म करना शुरू कर दी हर न्यू सेट ऑफ ब्लॉक के लिए, तो शिफ्टिंग से क्या होगा कि जो वैल्यूज़ हैं वो अपने एक कॉलम में नहीं रह जाएंगे, उनके कॉलम्स चेंज होते रहेंगे हर एक राउंड के बाद। वो कॉलम्स चेंज होने की वजह से एक बिट मल्टीपल बिट्स पे अफेक्ट करेगी, ठीक है। तो ये जो रिलेशनशिप आपको एक मिल गया था कि एक जो आपको एक पैटर्न मिल गया था कि आपके एक ही कॉलम में वैल्यूज़ रहना है, वो अब रहेंगे नहीं और वो पैटर्न कहीं ना कहीं ब्रेक हो जाएगा। और अच्छा, ये एक जनरल फार्मूला है, जनरल डायग्राम है हैश फंक्शन कैलकुलेशन का। इसको हम जनरली कहते हैं कंप्रेशन फंक्शंस, क्योंकि यहाँ पे कंप्रेशंस, अभी तो एक बहुत ही सिंपल आपको एक्सॉर और शिफ्टिंग ऑपरेशन दिखाया है, लेकिन यहाँ पर अगर हम SHA 512 बिट्स की अगर बात करें तो वहाँ पर हमें यहाँ कुछ कंप्रेशन फंक्शंस होते हैं, तो वो कंप्रेशन फंक्शंस भी हम देखेंगे बाद में, लेकिन अभी एक सिंपल सा ये ऑपरेशन है. If you talk about the attacks on the hash function, then if you have got an hash of length n, then the effort required for breaking the one-way property is that you have to calculate the brute force for all the 2 raised to the power n possible values. वीक रेजिस्टेंस को ब्रेक करने के लिए भी 2 raised to the power n वैल्यूज़ को जनरेट करना पड़ेगा आपको. बट एक हैरतंगेज चीज़ ये है कि स्ट्रॉन्ग कोलिजन रेजिस्टेंस will only require 2 raised to the power n upon 2, not n minus 1 but n upon 2 values to be generated in order to break this strong collision resistance. And why is that? We'll talk about it. If I just simply recall you that one way property says that from the message digest you won't be able to calculate the message. ठीक है, तो आपको इन्वर्स रिलेशनशिप बेसिकली फाइंड आउट करना है, तो आपको तो सारे के सारे ऑप्शंस एक्सप्लोर करने पड़ेंगे. अगर n बिट में रिजल्ट आ रहा है आपका, तो 2 raised to the power n values you will generate, and then you will match every value with the hash value that has been provided to you, and then you will be able to get the message, right? In weak collision also, the requirement was that I will be providing you with the message and the code, and then you have to find another message that produces the same code. So again you will have to generate all the possible values of the code, and you have to find that where that code is matching with the other values, and then we will be able to calculate the other messages as well, right? So again 2 raised to the power n combinations are required, but in case of a strong collision you need to find the pair of x and y that produces the same hash values. अब यहाँ पे पेयर टर्म आ गया है, तो वेरिएशंस जो हैं अब आपके 2 raised to the power n by 2 हैं. This will be explained in the next slide in greater detail. And most of the time the attacks on the hash function is generally performed in the compression boxes. इसकी vulnerabilities को स्टडी करके उस पर अटैक्स किए जाते हैं. तो different hash algorithms have got different kinds of attacks possible onto them. ठीक है, तो वो algorithm to algorithm vary करेगा, लेकिन हम brute force की अभी यहाँ पे बात कर रहे हैं. So the first two properties are very resistant to the brute force attack. Birthday attack की अगर हम बात करें, then this birthday attack is based on birthday paradox, and this birthday paradox is actually leading to 2 raised to the power n by 2 variations of the message only to get the to break the code. And how does that work? That if you have got a 64-bit hash code which you are using, so on an average the opponent would try to receive 63 messages, but if you are performing a birthday attack onto it, then the level of effort required is only of the order 2 raised to the power n by 2, and the value of n was 64, so 2 raised to the power 32. So 32 is much smaller number as compared to 2 raised to the power 63. Therefore we can say that we may think it is quite secure, but it is not that secure. Now what is this birthday attack? So in birthday attack, if you have got an m-bit hash code, you basically, the opponent tries to generate 2 raised to the power m minus 2 variations of those messages, and so these two set of messages are compared to find a pair of message that produces the same hash code. So by birthday paradox, the probability of the success is more than 0.5. So probability more than 0.5, that means it has got a good chance to calculate the values. Now why is that probability so high, even though I am using only 2 raised to the power m upon 2 variation of the messages? The reason is that the birthday paradox says that if you have got only 23 students in a classroom, and if you want to find out that how many students have got the same birthdays, then you would be able to find with a probability more than or equal to 0.5 the students who would be having the same birthday. The requirement over here is that you won't be able to tell the year that they are born in, but if I am talking about only the date and the month, so there are 365 possible values, and from those 365 values you have got only 23 students, and these 23 students you have to find that which of the two have got the same birth dates. Probability of finding such a result would be very less. But the problem over here is that we said in case of a strong collision that we need to find the pair of x and y such that the values of the code of x and the code of y are same, right? So if I am talking about the pairs over here, so these 23 students, so each student would be paired with every other student. So the number of pairs that are possible is 23 cross 23 minus 1 upon 2, right? So there are 253 pairs possible. You have to analyze these pairs. The pair count is huge as compared to the number of students. Since the number of pairs are huge, therefore there is a good probability that you would be able to find one such pair where birthdays are same.